In this video, we're going to talk about section 6.2, dealing with real applications of normal distributions. In the last video, section 6.1, we did talk about the standard normal distribution where the mean was 0 and the standard deviation was 1. Okay, here we're going to take this a little bit further in this section. Here we want to develop the ability to describe a normal distribution and not necessarily a standard normal distribution. Also, we'll find the probability of some range of values in a normal distribution and find X scores corresponding to regions under the curve representing a normal distribution. Okay, so in this case, when we're dealing with a normal distribution that is non-standard, that means the mean is different from 0 and the standard deviation is different from 1. Here we're going to have to convert that to a standard normal distribution by using the z-score formula. So that means we need to convert that x value to a z-score using this formula. And that is z is equal to x minus mu divided by sigma. And you're going to round your z-scores to 2 decimal places. Back in chapter 3, we did convert z-scores when we were talking about measures of relative standing. And some calculators in computer software programs do not require the above conversions to z-scores because probabilities can be found directly. So here we're going to be using table A-2 in this video to find probabilities. So that means we are going to convert values, our x values, to standard z-scores. Okay, and this is just an illustration of that. On the left, you have a non-standard normal distribution where the mean and the standard deviation are different from 0 and 1 respectively. Here, when we convert using z is equal to x minus mu all divided by sigma, it would become a standard normal distribution where the mean is 0 and the standard deviation is 1. Now keep in mind your z values can be either positive or negative. Okay. So here's the procedure for finding areas with a non-standard normal distribution. Number one, you want to sketch a normal curve and then label the mean and any specific x value. Then shade the region representing the desired probability. Number two, for each relevant value or relevant x value that is a boundary for the shaded region, you're going to use formula 6-2 to convert that value to an equivalent z-score. Okay, that was formula 6-2, which is what I just got through talking about. Z is equal to x minus mu all divided by sigma. The z value will be the 2 decimal places. Then you're going to use computer software or calculator or table A-2 as we will use in this video to find the area of the shaded region. This area is the desired probability. Okay. So now let's look at example 1. Post rates of women are normally distributed with a mean of 77.5 beats per minute and a standard deviation of 11.6 beats per minute. Answer the following questions here. What are the values of the mean and standard deviation after converting all post rates of women to z-scores using z is equal to x minus mu divided by sigma? Now, that question is going to be quite tricky, but here it is. When you convert post rates to z-scores, that's going to mean that your mean will be 0 and the standard deviation is 1. That's how you'll answer that question. Because after you convert those post rates to a corresponding z value, then that means using the standard normal distribution, your mean is going to be 0. That's the center of the data. The standard deviation will be 1. The original post rates are measured with units of beats per minute. What are the units of the corresponding z-scores? Anytime you convert to a z-score, z-scores will never have a unit of measurement. So it's going to be this answer choice here. Z-scores are numbers without units of measurement. Okay. All right, now let's look at example 2 here. Find the area of the shaded region, and then, the graph of the to the right, or right here, depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and the standard deviation of 15. So here we're trying to find the probability that an individual, a randomly selected individual, has an IQ score less than 75. And I did say less than because the area to the left is shaded. So our X value there is 75. And we're told that the scores are normally distributed with a mean of 100. That's your mu. And the standard deviation, sigma, is 15. So now we need to convert 75 to an equivalent z value. Using that z formula, z is equal to x minus mu. The whole thing's divided by sigma. Your x value is 75 minus mu, that's 100, divided by sigma. The standard deviation is 15. Now, if I do 75 minus 100, that's going to be negative 25. And if I do negative 25 divided by 15, you're going to see we're going to get a negative number, negative 1.6 repeating. To 2 decimal places, this will be a negative 1.67. Okay, that's our z value. Now we're going to use that to find the area to the left, which is what we want. So I need to look under the page that says negative z-scores, because that z value is obviously to the left. Negative. So here's negative 1.6 and then 0.07. If I go across the negative 1.6 in the row in the column for 0.07, I have 0.0475. So that means, and that's exactly what I was looking for. This means that the probability that x is not going to be z this time is the x value. The probability that x is less than 75 would be 0.0475. So that means that the probability of randomly selecting an adult with an IQ score less than 75 would be 0.0475. Okay. All right, here's another example. Say I want to find the area of the shaded region. The graph here depicts IQ scores, and those scores are normally distributed with a mean of 100 and the standard deviation of 15. So I'm trying to find the probability of randomly selecting an adult whose IQ score is between 75 and 100. Notice I have 2 X values here. I'm finding the area that's in between those. And I do know that the mean was 100 and the standard deviation is 15. That's given to us in the problem. All right, so now I need to convert each one of these to z-scores. So let's start off with the 75. The z-value, of course, is x minus mu divided by sigma. Here the x is 75 minus mu, which is 100, divided by 15, which is the standard deviation. Now 75 minus 100 is negative 25. And negative 25 divided by 15, I think I did this in the last example. That's negative 1.67, rounded to 2 decimal places. And now for x equal to 100, using that same formula, okay. So here, x minus mu, that's 100. This time the x is 110. Okay, I need to change this because that's 110 for x. So here the x is going to be 110 minus the mean of 100 divided by the standard deviation of 15. So 100 from 110 will be 10. 10 divided by 15. That's going to be 0.67, rounded to 2 decimal places. Okay, so those are my z-values here. For each one of these, I'm going to find the area to the left. So for, let's see, z equal negative 1.67. That's this value here. And I want the area to the left. And that's a negative z-score. So find negative 1.67 on the table. There's negative 1.6 and then 0.07. Read across and down. That area to the left would be 0.0475. Okay. Now for z is equal to positive 0.67. It's a positive z-score, so we have to look at the page that says positive z-score for table A-2. Okay, so 0.67 is 0.6 right here, 0.6, and then 0.07 is over here. So read across and down, that's going to be 0.7486. Okay. Now, as you know, when we're finding the area in between, we have to subtract those probabilities here. So the probability that some x value is between 75 and 110, we subtract 0.7486 minus 0.0475. If I subtract those two, you'll get 0.7011. That would be that shaded area there. So to put that in perspective, the probability of randomly selecting a adult with an IQ score between 75 and 110 would be 0.7011. Okay, here's another example. Assume that adults have IQ scores that are normally distributed with a mean of mu is equal to 100 and the standard deviation sigma equaling to 15. So that's given to us. Mu is equal to 100. Standard deviation is 15. Find the probability that a randomly selected adult has an IQ score less than 118. Okay. So that mu is equal to 100, that's at the center. And I'm going to say 118 is somewhere to the right of that. Say about right here. And it says less than 118. So that means we need to shade to the left of 118. I'm going to shade this in red. So that's the shaded area to the left. That's what we're looking for here. So in other words, we're going to find the probability that X is less than 118. That's what we're looking for. Now we need to convert 118 to a Z value. Okay. So for X is equal to 118, our Z is equal to X minus mu divided by sigma. That's what we use to convert to a Z value. Your X is 118 minus mu, which is 100, divided by sigma, that's 15. So 118 minus 100, that's 18. And 18 divided by 15, if we carry this out to 2 decimal places, this will be 1.2. But to 2 decimal places is going to be 1.20. Now that's what we will use to locate the area to the left in table A-2. And we have a positive Z value. So we look under the page for positive Z scores and find 1.2. And then you got 0.00 right here. So read across to 1.2, the column for 0.00, this will be 0.8849. And it does say cumulative area to the left, which is exactly what we're looking for in this case. So the probability that X is less than 118 would be 0.8849. And to put that in perspective, the probability that a randomly selected adult with an IQ score less than 118 would be 0.8849. Okay. Now this is, of course, you have to convert to a Z-score and then use table A-2 to find the appropriate probability value. Okay. And keep in mind, if you were looking for the area to the right, where if this was a probability that X is greater than 118, then you'll take this and subtract 1 from it. Okay. And here's one more example. Assume that adults have IQ scores that are normally distributed with a mean of mu equaling to 105 this time. So here they changed it a bit. And the standard deviation of 20. Change that a bit as well. Find the probability that a randomly selected adult has an IQ between 89 and 121. So in this case here, the mean represents the center. That would be 105 at the center. 89 would be to the left of 105. So I'm going to say 89 is about right here. And then 121 would be somewhere over here to the right of 105. I'm going to draw my boundary lines. The area we're looking for is in between those two. Okay. So let's start by converting the 89 and 121 to z-scores. So for x equals 89, we use this formula, z is equal to x minus mu, all divided by sigma. Yeah, x is 89, so that's 89 minus, the mu is 105, divided by sigma, which is 20. So if I do 89 minus 105, that's going to be negative 16. Negative 16 divided by 20. And I'll carry this out to 2 decimal places. And that's going to give us negative 0.80. So I'm going to use that to find the area to the left. And I'm going to use the table for negative, the page that says negative z-scores. The negative 0.8 is way down here. 0.0 is this first column. 0.00 is that first column. So read across and down this first column where it says 0.00, that'd be 0.2119. So the area to the left, this is area right here to the left of that, would be 0.2119. That's this area to the left right here, 0.2119. And now for x equal 121. Also, that z-score formula is still the same, but this time x is 121 minus mu, which is 105, divided by sigma, which is 20. Now, 121 minus 105 is going to be 16. 16 divided by 20 would be positive 0.80. And now we want the area to the right. Not to the right, to the left. Because the table is the cumulative area to the left. Let's find 0.80. Using the page that says positive z-scores. Okay, here's 0.8. 0.00 is that first column. Read down to the right. It'll be 0.7881. So that's the area to the left. And to illustrate that, 0.7881 is this area to the left. So here is that area to the left. We want the area in between those two values. So to get that area in between, we have to subtract. So now the probability that our x is between 89 and 121, we subtract 0.7881 minus 0.2119. And that would give us 0.5762. 0.5762. And what that means here is that the probability that a randomly selected adult has an IQ between 89 and 121 will be 0.5762. Okay. So these examples that I just did dealt with where you have to convert your x values to a corresponding z value and use table A-2 to help you find your probabilities. Now we're going to go the other way around. Here we're going to find values from known z-scores and find values from known areas. So here's some helpful hints that may help when you're finding those relevant values. Do not confuse z-scores and areas. Keep in mind the z-scores are the distance along the horizontal scale, but areas are just regions under the normal curve. And table A-2 lists z-scores in the left column and across the top row, but areas are found in the body of the table. Keep that in mind. And number two, you want to choose the correct or the right or left side of the graph. A value separating the top 10% from the others will be located on the right side of the graph, but the value separating the bottom 10% will be located on the left side of the graph. Keep that in mind. Also, a z-score must be negative when it is located in the left half of the normal distribution. In the last video for section 6.1, I did mention if you have a decimal value that's less than 0.5, you have to use the page that says negative z-scores. If it's at least 0.5, then you use the page that says positive z-scores. Areas or probabilities are positive or zero values, but they are never negative. Okay, very important. Next, we get the procedure for finding values from known areas of probabilities. These are only the first two. The remaining will be on the next page. Number one, you want to sketch the normal distribution curve. Enter the given probability or percentage in the appropriate region of the graph and identify the x values being sought. Then second, use technology if needed. If you're using table A-2, you want to refer to the body of the table of A-2 to find the area of the left of x, and then identify the z-score corresponding to that area. All right, on the next page are steps 3 and 4. If you know z and must convert it to an equivalent x value, if you know z, you must convert it to the equivalent x value. This is where we use formula 6-2 by entering the values for mu, sigma, and the z-score found in step 2. Then solve for x. Based on the formula 6-2, we can solve for x as follows. And that's going to be this. X is equal to mu plus the product of z and sigma. This is just another way of writing formula 6-2. They did this algebraically to get x by itself. And if z is located to the left of the mean, be sure that it is a negative number. And do keep in mind you can have a negative z value or a positive z value. And this is the formula we'll use to find out what our x values are going to be. And then refer to the sketch of the curve to verify that the solution makes sense in the context of the graph and in the context of the problem. Okay. Now, here's some things we need to consider. We should always draw a graph to visualize the information. It does help to draw a normal curve and then fill in the information. That way you can see what's going on. We should determine whether we want to find the area or a value of x. Regardless of the situation, we must usually work with a cumulative area from the left. And we should know that a z-score and x value are distances along horizontal scales, but percentages or probabilities correspond to areas under the curve. So now let's apply this procedure to example 8. Okay, here it is. Let's say I want to find the indicated IQ score. The graph here depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. Now notice, you're given an area to the right. That's the shaded area, which is of course 0.85. If we're going to use table A-2, we need to know this unshaded area on the left because it calls for the cumulative area to the left. So now, let's find the area to the left. And the area to the left is this. The whole area underneath the entire normal curve is 1. We're going to subtract from it 0.85. So 1 minus 0.85 would be 0.15. And notice I'm going to add 2 zeros behind it because our body of the table is the 4 decimal places. So this area here is 0.1500. We're going to use 0.1500 to find out what our corresponding z value is going to be. And notice 0.1500 is less than 0.5. We need to use the page that says negative z-scores. Okay. So we're going to find a value that's closest to 0.1500. And I'm going to use 0.1492, which is this right here. So now I'm going to look for the row in the column that 0.1492 is in. The row that is in is negative 1.0. The column that is in is going to be 0.04. Okay, so my z is this. Put the negative on the outside, and it was 1.0. And then plus in the column 0.04. Add those together, you'll get a negative 1.04. So that's the z value that we're going to use here. But we're looking for the x value. That's the indicated IQ score. So that's where we use this formula here. X is equal to mu plus z times sigma. That's this formula that I just showed you right here. That's going to help us find that corresponding x, that x value. Now, in this case, we need to know what our mean is. We're given that the mean is 100, so that's your mu. And your standard deviation, sigma, is 15. And we know what z is. That's negative 1.04. So we're just going to substitute into this equation to find x. So x is equal to mu, which is 100, plus z, that's negative 1.04, times sigma, which is 15. Now we can type all this in the calculator here. So if I do 100 plus the negative key is down here. You'll press that button. Do not confuse that negative key with the minus symbol. The negative key is at the very bottom, a small minus sign with the parentheses in it. And then 1.04 times 15. That will be 84.4. Now, what that 84.4 means, that is the indicated IQ score. That we were looking for. And that separates the bottom 15% from the top 85%. If we want to take that a little bit further. All right, here's another example. That's this. Engineers want to design seats in commercial aircraft so that they are wide enough to fit 95% of all males. Accommodating 100% of males would require very wide seats that would be much too expensive. Men have hip breadths that are normally distributed with a mean of 14.2 inches and a standard deviation of 1.1 inch. Find P95, and that represents the 95th percentile. In other words, you want to find the hip breadth for men that separates the smallest 95% from the largest 5%. Okay, so here's my bell-shaped curve. 95% will have to be somewhere over here because that's most of the normal curve. Okay, so this is the X value we're looking for. And we're told that the mean is 14.2 inches. And the standard deviation is 1.1 inch. So if I draw my boundary line, I'm looking for the bottom or the smallest 95%. That's a shaded area right here that I want. And this, in this case, is 0.9500. If you recall, 95% as a decimal will be 0.95. And since I'm dealing with a table with 4 decimal places, I'm going to put 2 zeros behind it. All right, now let's find 0.9500 in the table so we can come up with our Z value. And that's bigger than 0.5, so we need to look at the table that says positive Z-scores. Well, I see 0.9495 and 0.9505, but in between those, notice you see an asterisk. Let's follow that asterisk down to this bottom left-hand side of the table. Take a look. That area, 0.9500, the corresponding Z-score for it is 1.645. That's one of those special cases that I talked about in the last video for section 6.1. That Z value is 1.645. And now we can find out what X is using X is equal to mu plus Z times sigma. Z is the Z-score, sigma is your standard deviation, the mu is the population mean. And our mu is 14.2, so we just substitute 14.2 plus Z, which is 1.645, times sigma, that's 1.1. Okay, so I'm going to enter 14.2 plus 1.645 times 1.1. Now let's say we want to round this off to 1 decimal place. Okay, now in the homework, they will tell you how many decimal places they want you to round your final answer to. So in this case, to 1 decimal place, it will be 16.0. Now that 16.0 represents the hip breadth for men, separating the smallest 95% to the largest 5%. And this should be inches. Okay. Because our hip breadth is measured in inches in this case. All right, now example 8. Assume that adults have IQ scores that are normally distributed with a mean of 102.4 and a standard deviation of 21.1. Find the first quartile, which is Q1. And that is going to be the IQ score, separating the bottom 25% from the top 75%. And a good way to do this is draw a graph. Okay, if you recall Q1, back when we were talking about relative standing, Q1 is the 25th percentile, separating the bottom 25% from the top 25%. So I'm going to say right here is what we're looking for, our X value. And the shaded area that's the 25th percentile. And of course, 25% as a decimal will be 0.25. I'm going to add 2 zeros behind that. And I'm also going to mention that the mean was 102.4 as given in the problem. And the standard deviation, sigma, was 21.1. So now we need to find, in this case, 0.2500. That's less than 0.5. So we need to look under the page that says negative z-scores. Okay. So we need to find a decimal value in the body of the table that's close to 2,500. I'm going to use this one, 0.2514. That looks closest to 0.2500 than 0.2483 is. So let's use 0.2514. The column, the row that it's in is going to be negative 0.08. I'm sorry, negative 0.6. The row it's in is negative 0.6. The column that it's in is going to be 0.07. Okay, so our z is this, negative, and I'm going to put this in parentheses, 0.6 plus 0.07. That's going to end up being negative 0.67. That's the z value for the 25th percentile, negative 0.67. Now I need my x value for that. So this is where I use x is equal to mu plus z times sigma. And x is going to be this. The mu is 102.4 plus z, we found that out to be negative 0.67 times sigma, 21.1. So in the calculator, 102.4 plus negative 0.67 times 21.1. Let's say I want to round this out to one decimal place. So that x value to one decimal place, this 6 would make that 2 or 3. So it'd be 88.3. 88.3. And that represents a IQ score separating the bottom 25% from the top 75%. Okay. Now let's look at this example, a little bit more complex than the others. So it's a survey that found women's heights are normally distributed with a mean of 63.8 inches and a standard deviation of 2.3 inches. A branch of the military requires women's heights to be between 58 inches and 80 inches. And this is a two-part question. In part A, find the percentage of women meeting the height requirement. And are many women being denied the opportunity to join the military, this branch of the military, because they are too short or too tall? And then part B, if this branch of the military changes the height requirements so that all women are eligible to, let me read that again. If the branch of the military changes the height requirements so that all women are eligible except the shortest 1% and the tallest 2%, what are the new height requirements? Okay, so this is a two-part question or problem. All right, let's start with part A. So here we're going to find the percentage of women meeting the height requirements. Okay, so our mean was 63.8 inches, and the standard deviation is 2.3 inches. So the branch of the military requires women's heights to be between 58 and 80 inches. So if this is 63.8 at the center, then 58 will be about right here, and 80 will be somewhere over here. So in this case here, we're looking for this shaded area right here. So now we got to find the Z values for both 58 and 60. Okay, here we go. Let's start with X equal 58. And of course, the Z is always going to be X minus mu divided by sigma. Your X value is the 58 minus mu, which is 63.8. That was given to us, divided by the standard deviation of 2.3. So 53 minus 63.8 would be negative 5.8. And then 5.8 divided by 2.3. And I know that's going to be negative, so we always round our Z values to two decimal places. Negative 5.8 divided by 2.3. That's going to be, negative 5.8 divided by 2.3. So to two decimal places, this will be negative 2.52. Negative 2.52. And for that, we want the area to the left. And it's a negative 2.52. So, negative 2.52. We need to use negative Z-scores. The page for that. Let's see, negative 2.5 is right here. And 0.02 is here. Go to the right and down. That would be 0.0059. That represents the area to the left. And now let's find the Z value and the area to the left where X is equal to 80. Using that same Z formula, X minus mu divided by sigma. This time your X is going to be 80. 80 minus the mu of 63.8, all divided by sigma, which is 2.3. So 63.8 from 80 is 16.2. 16.2 divided by 2.3. And we want this to two decimal places. So 16.2 divided by 2.3. This would be 7.04. Let's try to look for the area to the left of that. Okay, and 7.04 is positive, so we need the area. We need to look at the page that says positive Z-scores. We're going to have a problem with this one This goes up to 3.49. But notice that it says here 3.50 and up would be this. So with a 7.04 Z value, that area to the left, we're going to have to use 0.9999. .04 is bigger than 3.50, so we have to use 0.9999 as the area. But here, the probability for that Z value, that's very small, a lot small. So now, to find the probability between those two, the probability that a woman's height is between 58 inches and 80 inches, we're going to subtract 0.9999 minus 0.0059, and you'll get 0.9940. Okay. And it does say find the percentage of women meeting the height requirement. And in this case, if I convert that to a decimal, that would be 99.4%. So 99.4% of all women meet the requirement. Now, are many women being denied the opportunity to join this branch of the military because they are too short or too tall? And the answer for that would be no. Because if you look at 99.4%, subtract that from 100%, that'd be like 0.6%. That's very small. So here we can say that no, only a small amount do not meet the requirement. And that's just a very small amount. The women do not meet the requirement. So that's part A. Part B says here, if this branch of the military changes the height requirement so that all women are eligible except the shortest 1% and the tallest 2%, what are the new height requirements? Okay. Now to do this, I'm going to go and draw a normal curve for this one. I wish I had one of my own that I could have pasted on here. Now here the mean and the standard deviation are going to be the same as part A. So that mean, of course, is 63.8. And the standard deviation is 2.1. The smallest 1% would be somewhere to the left. I'm going to label this as X1. The tallest 2% would be somewhere over here. I'll label that as X2. So this represents the smallest 1%. And as a decimal, 1% would be 0.01 with 2 zeros behind it. This represents the smallest the largest 2%, or the tallest 2%. 2% as a decimal would be 0.02 with 2 zeros behind it. Okay, so now we're going to find out what X1 and X2 are going to be. Let's start out with X1. So for the area of 0.0100, we need its corresponding z value. It's a negative, it's less than 0.5, so we need, in this case, the negative z page. That's this. We're going to find a decimal value that's close to 0.0100. Let's try, I'm going to try 0.0099. That's a little less than 0.0100. Let's use that. The row that is in would be negative 2.3. The column that is in 0.03. So the z value is going to be negative 2.33. And then to find what x1 is, that's going to be mu plus z times sigma. And our mu is 63.8 plus z, which is negative 2.33 times sigma 2.1. And we're going to round this answer off to one decimal place. So 63.8 plus negative 2.33 times 2.1. Let's see, this is 58. I don't know why I'm getting 58.9. Let me try it again, 63.8. Oh, this should be 2.3. Because the standard deviation is 2.3. What did I get? 2.1. This should be 2.3 also. Okay, so let's try that again. 63.8 plus negative 2.33 times 2.3. This would be approximately 58.4. Okay. This should be 2.3. So you want to make sure that your mean and your standard deviation when you copy it down is correct. So we know this is going to be 58.4. But what about x2? Let's see here. For the area of, and in this case, the tallest 2% or 0.0200. I want the area. Notice that this is the area to the right. If I'm going to use the table, I need the area to the left. So this is where I need to do 1 minus 0.0200, which is going to be, in this case, 0.9800. And I will show you. This right here, the area to the left, that's going to be 0.9800. It's that value that I need to look for in the table. And it's greater than 0.5. So we need to use the page that says positive z-scores. So we're going to find a value close to 0.9800. And in this case, let's use 9798. That's close to 0.9800, 0.9798 right here. The row that it's in is 2.0, and the column that it's in is 0.05. So we got 2.05 as our z value. So, and Z is equal to 2.05. That's our Z value. So now to find X2, which is this boundary value there, we're going to use mu plus Z times sigma. Your mu is 63.8 plus Z is 2.05 times the standard deviation of 2.3. So in this case here, 63.8 plus 2.05 times 2.3. This will be approximately, to one decimal place, 68.5. So this is X2. So in this case here, if the branch of the military changes its height requirements to allow all eligible women except the shortest 1% and the tallest 2%, then their height requirements will have to be between 58.4 inches and 68.5 inches. Okay. So those are the new requirements here. So those new height requirements are the women must have heights between 58.4 inches and 68.5 inches in order to join this branch of the military. Okay. All right, now let's look at this last example, example 10. This deals with lengths of pregnancies. The lengths of pregnancies are normally distributed with a mean of 270 days and a standard deviation of 15 days. Part A is to find the probability of a pregnancy lasting 309 days or longer. And B, if the length of a pregnancy is in the lowest 3%, then the baby is premature. Find the length that separates premature babies from those who are not premature. Let's start with part A. The mean is 270 and the standard deviation is 15. So 270 is your mu, the standard deviation is 15. Let's see, we're trying to find the probability of a pregnancy lasting 309 days. So I'm gonna say 309 is over here somewhere. 309 days or longer. That means the area we're looking for is on the right, not the left, the right, because 309 days or longer means more than 309 days. So now we want to convert this to a Z value. So we're at X equal to 309. Our Z is going to be X minus mu divided by sigma. Part A, you have to convert to a Z value. So your X is going to be 309. That's what X is, minus mu, which is 270, divided by sigma, which is 15. Subtract 270 from 309, you'll get 39. 39 divided by 15, I'll show you on the calculator, that would be 2.60. Carried out to 2 decimal places. You always carry your Z values to 2 decimal places. Now we're going to use that to find the area to the left, because our table specifies the area to the left. 2.60 is positive, so let's use the positive Z page and find 2.6, which is over here, and 0.0 is that first column. So 2.6 across and down gives me 0.9953. But keep in mind that 0.9953 corresponds to the area to the left. I want this area to the right. So I need to subtract 1 minus that to get the probability that x is greater than or equal to 309. As it says 309 days or longer, so I need to use the inequality greater than or equal to 1 minus 0.9953. Keep in mind the area underneath the normal curve is 1, so 0.9953 from 1 would be 0.0047. So that means the probability that a pregnancy lasting 309 days or longer would be 0.0047. That's a very small probability for that to happen. Okay, now on to part B is this. If the length of a pregnancy is in the lowest 3%, then the baby is premature. And we want to find the length that separates the premature babies from those who are not premature. And in this case, I'm drawing a normal curve. The mu is going to be at the center, where mu is 270. And your standard deviation is still going to be 15. Let's say x is over here. Because 3% is a small probability. So here, this area represents the 3%. The smallest 3%. 3% as a decimal will be 0.03 with 2 zeros behind it. So now I need to find out that corresponding C value for it. Using table A-2, 0.0300 is less than half. We need to use the page that says negative z-scores. So in this case here, we're going to find the value that's closest to 0.0300. Let's use 0.0301. That's close to 0.0300. So the row that 0.0301 is in is negative 1.8, and the column that is in is going to be 0.08. Negative 1.88 is our z value. And now we want to find out what that x value is going to be. Using x is equal to mu plus z times sigma. So here x is equal to, your mu is going to be that 270, which is the mean, plus z, negative 1.88, times your standard deviation sigma, that's 15. Okay, in this case here, 270 plus negative 1.88 times 15. Now I get 241.8. But since we're dealing with days, we're going to round this up to the nearest whole number. Has to be 242. Okay. So the length of pregnancies that separates premature babies from those who are not premature would be 242 days. Okay. Right. So the first part, you have to find out the probability. The B part, you have to find out what the x value is given the known area. Okay. There's one more thing I'm going to cover. These are the z tables for negative and positive z-scores. It's a flowchart that I found dealing with applications with normal distributions here. Okay. So here we're going to start with finding, what do we want to find? We either want to find the probability from a known value of x, or we want to find the value of x from known probability or area. Now, we're finding the probability from a known value of x, then we need to ask ourselves, are we using technology or table A-2? Now, if you're using table A-2, like we did in this video, then you're going to convert to a standard normal distribution by finding z first, using the formula z is equal to x minus mu divided by sigma. And then you look up your z in table A-2 to find the cumulative area to the left of z. And if it's the area on the left you're looking for, you use that value. If it's the area to the right, then you have to subtract 1 minus that cumulative area from the left. If you're given two x values, each one you find the cumulative area to the left and subtract those two probabilities to get the area in between. Or if you're using technology, you'll find the probability by using the technology. It could be with the TI-83 or 84 plus calculator or stack disk or whatever. But let's say you're finding a value of x from a known probability or area. Then you're going to identify the cumulative area to the left of x like this. And if you're using technology or table A-2, well, you're going to be using one or the other. But if you're using technology, you'll just find the x directly from that technology. But let's say you're using A-2, like we did here. You want to look up that cumulative left area in table A-2 and find the corresponding z-score. And then solve for x using x is equal to mu plus z times sigma. Okay. And I understand that this is a lot that we covered in section 6.2, dealing with probabilities for normal distributions and how to apply those, in this case, to real life situations here. But do feel free to email me, or, if you have any questions about this particular lesson, and do get some practice on this section in the homework. So that will conclude this video on real applications of normal distributions.